Good morning, everybody, or afternoon, depending on when you may be watching this vodcast. Today we are doing the lecture for statics, section 2.2. As you notice, I'm doing this from my office rather than the classroom, but the lecture material is the same. The first thing I wanted to let you know is about your homework, and I have graded your first homework assignment, which is the conversion factor handout. We have 7 students in this class, and only 4 of you have turned them in. So I would really encourage the other 3 of you to get that homework done and turned in via Moodle as soon as possible so that you can get credit. I won't remove credit if you turn it in within a reasonable amount of time, but I'd really like to see that from everybody. So please work on your homework. The next thing is here on our Moodle page, you can see that I have a link for lecture 4, which was section 2.1, where we started working with vectors. Today I'm going to be recording lecture over section 2.2, which is lecture number 5. So by the time you see this, there will be a link here. The other thing is I'm going to work out a couple of homework problems. So underneath the link for lecture 5, I'll have some notes, and the notes are going to be worked out lecture problems. So it's pretty easy if you'll take the notes and go through the assignment, my vodcast, while you're looking at the notes, then you'll be prepared to do your homework. So having said that, I'm going to go over a couple of PowerPoints that I have for this material. And last time we talked about forces, and we talked about the fact that forces are vectors, and that in order to add them together, we need to add them by components. So in other words, if we're using rectilinear system, we need to break them down into the x component and the y component, and then we can add them to a sum as long as we do the x piece and the y piece together. So we did a couple problems like that on the last vodcast. And if you have any questions, we're going to be doing this for an awfully long time. So I really want to make sure that you are comfortable with that whole idea. So here are some ideas of how forces add together graphically. And we're not really going to spend any time on that because we instantly go from a graphical to a vector math method. And so for section 2.1, we used vector math, and we will use vector math rather than a graphical solution from here on out. So the first part is, if you have 2 vectors here, P and Q, the idea is that the resultant, or the vector sum of P and Q, which we call R for resultant, has the same effect on point A as if we have 2 forces. So we can have 2 forces, P and Q, or we could apply one single force, R, which is the vector sum of P and Q, and that would have the same effect. And that's sort of the reason that we're getting at this. In dynamics, we use Newton's second law in the form of F equals ma. So the sum of the vector forces is equal to mass times the vector acceleration of an object. Now in statics, where we're aiming at is the idea that if a particle or a body, rigid body, is sitting still, the vector sum of the forces in each direction, in this case x and y, has to sum to 0. So we don't have to think about acceleration in the sense that F equals ma, because since a is equal to 0, the vectors will sum to 0. All the force vectors will sum to 0 in the x and the y direction. We can use that to find unknown forces. So for today, what we're doing is we're just talking about adding forces, P and Q, and coming up with a sum. So the graphical solutions are shown on these slides. Now, similarly here, if we look at this, we have a barge that's being pulled by 2 tugboats. That means that if we look at point B, that we have a force AB, which is the tension in this rope, and the force BC, which is the tension in this rope. And if we break it down into x components and y components of A, so in other words, A sub x, A sub y, C sub x, C sub y, then we can say that the resultant would be the same as if we had a single tugboat pulling with that force in a particular direction. And that's the upshot of what we're getting to today. So these slides once again just talk about the graphical solution to that. Now we talked last time, and this is the method that we're going to be using from now on, that a force is equal to the force components in the x and y direction, and we use the letters I and J to indicate the directions. Now there's a lot more to that. These are called unit vectors, and we're going to learn more as time goes on. But if we do a resultant force this way, regardless of how many forces we have operating on a point or an object, we can add them together as long as we group together the x components, group together the y components, and then we can find the r sub x component and the r sub y component. Now the other thing is that since x and y are perpendicular to each other, we can also use the theorem of Pythagoras to find the magnitude of the resultant and the direction of the resultant. And to be honest with you, this is the crux of what we do in statics for an awfully long time. We extend this discussion to a lot of different scenarios, but breaking forces up into components and adding them together into resultants is kind of the first most primary skill, and we keep doing it all semester long, and you'll do it later in dynamics and mechanics of materials and probably physics as well. So sample problem 2.3 talks about this idea. We have f sub 2, f sub 1, f sub 3, and f sub 4, and they ask us to determine the resultant force on bolt A. So what they're really saying is, what is the one single force we could have that would replace F1, F2, F3, and F4 in terms of what effect it has on A? So we take each of those four forces, break it up into x and y components, and then we add them together vectorially, keep the x components together, the y components together, find the magnitude and the direction. Now, just a couple of points. If you look at F1, you look at the orientation of the x and the y axes. Generally speaking, x is considered positive to the right, y is considered positive up. So F1 has a positive x and a positive y component. F4, on the other hand, has a positive x but a negative y component. F3 has no x component at all, or the x component is 0, and the y component is negative. And force 2 has a negative x and a positive y component. So on the next slide, you'll see the way that we've broken this up. They keep in mind those signs. And then they just, after we do the x and the y, breaking it up using sines and cosines, we can just add the values, and we come up with an r sub x of 199.1 in the units of newtons, and an r sub y of 14.3, once again in units of newtons. So our resultant, the magnitude of the resultant, is that value, 199.6. In other words, using the Pythagorean theorem to find the hypotenuse of that triangle at an angle of 4.1 degree. Now, if you do it this way, you have to reference the angle from something. You have to reference it from, in this case, horizontal. But if you write a vector in this form, you need to reference what that angle alpha is measured from. And drawing a picture, to me, is probably a wonderful way to do that. All right, now the next slides talk about the equilibrium of a particle, which is just what we've talked about before, that we have, if a particle is not moving, in other words, if the particle is at equilibrium or in equilibrium, then the sum of the forces in the x direction will be 0, and the sum of the forces in the y direction will be equal to 0. So we're going to save that for our discussion of section 2.3, and today I'm just going to work a problem for you showing you how to do this with multiple forces. So in your textbook there are several problems, and I've assigned 3 of them. These are quite lengthy and they take a little bit of time, so I've assigned them in your it's in your homework assignment for chapter 2, which will be due in, I don't know, a couple weeks or something like that. So I want to work at least one problem to introduce some of these concepts to you so that you have these in your notes. Today I'm going to be working on problem 2.23, and as I said, I'm going to work this on the video, but when you're watching this video, please pull up the notes, which will show you the steps that I'm taking. All right, so problem 2.23 shows a hook of some sort that is being acted upon by three forces. And so I draw the x and the y axis, showing the origin where the forces go through in terms of the hook. And we have a force that is acting off to the left, up and to the left, at an angle of 35 degrees from the horizontal, and that has a magnitude of 150 newtons. We then have a force acting up and to the right, which has a magnitude of 80 newtons, acting at an angle of 40 degrees from the horizontal, and then a third force with a magnitude of 120 degrees, or 120 newtons, acting 30 degrees from the 80 Newton force, which means that it's acting 70 degrees from the 70 degrees from the horizontal. So the first thing that I want to do, just like on the chart here, I want to write out which the names of the forces are, write their magnitude, and then find the x component using sines and cosines, find the y components using sines and cosines, and be careful to keep the signs. In other words, the 150 Newton force is up and to the left, so it's a negative x and a positive y. The other two are both positive x and positive y. All right, so I draw my little chart, force 1, force 2, and force 3, which I will have to label. These are not labeled as being 1, 2, and 3. So the 150 force is force 1 in my nomenclature. There's no right or wrong to that. There's the 120 Newton force is force 2, and the 80 Newton force is force 3. So after that, I write the next column, which is the x component, and then the final column, which is the y component. All right, so if I look at the 150 Newton force, the first thing I see is that it's negative in the x direction, positive in the y direction. The magnitude in the x direction, because the cosine is with the horizontal, is going to be negative 150 times the cosine of 35 degrees. The y component is going to be positive 150 times the sine of 35 degrees. Now you could also say that it is the cosine of 55 degrees, but since this is broken out for us, there's no reason to do so. I'm going to skip down to force 3, which is the 80 Newton force, because it's 40 degrees from the horizontal, and it's positive both x and y. It's going to be 80 times the cosine of 40 degrees. It's the magnitude in the x direction, and it's going to be 80 times the sine of 40 degrees in the y direction. Now for the 120, even though the angle shown on the diagram is 30, because that's 30 degrees from the 80 Newton force, the angle from the horizontal, which is what I want to reference, is 70 degrees. So the magnitude of the x component is 120 newtons times the cosine of 70 degrees, and in the y direction, it's positive 120 times the sine of 70 degrees. All right, so now I have all three of the components. I need to take my calculator, and maybe I could put one on the screen. I need to just get a calculator and do that math really, really quickly. So the one thing I want to ask you to do, if you are working with sines and cosines, make sure that your calculator is set to degrees, not radians, because if you use radians, you're going to get some strange answers. So the first thing I want to do is to find out what is the cosine of 35 degrees. So I just type that into my search bar. Now I could just use a calculator like this, but the cosine, do you see this right here? I want to show you. It's come up as being radians, which is a default for a lot of math functions. Now, so you have to tell it it's going to be degrees. So here you see that this calculation is the cosine of 35 degrees. And if you're going to use your calculator, you can just hold that in place and keep all the decimal places. Almost all cosine signs, almost all trig functions are irrational numbers, so they'll go on and on forever. But I'm just going to round this off to 8.19. So the next thing I'm going to do then is to say I want to take the sine of 35 degrees, and I need to make sure that I am, hang on a second, 35 degrees. See, this is in radians again, so I want to put this into degrees. The sine of 35 is 0.573. And like I said, this will all be on my notes, so you'll see how to lay it out. So 0.573. So the next thing that I want to do is take the cosine of 70 degrees. And of course, we want to see if it pops back into radians. Nope, we're good. So the cosine of 70 degrees is 0.342. And the sine of 70 degrees is 0.774. Okay, and then finally we've got the cosine of 40 degrees, and then the sine. See, that went back to radians again, so we need to go right there. 0.766. And the sine of 40, 0.643. All right. So then when I do my multiplications, once again, take a look at your at the table that I'm constructing in the notes. So I have the sine of 40 degrees, and I want to multiply that by the magnitude of that third force, which is 80, and I get 51.4. And the next one, I have 120 times, I'm working my way up, 120 times the sine of 70, which is 0.774. And that value then is 92.88, which is 92.9, more or less. And finally, I have 150 times the sine of 35, which is 0.573. And that's 85.95. So, so would you round that up or down? I round 5s up, and that has to do with measurement, because measurements of 0 are not exact, which is sort of what you assume if 5 goes up or down. So I always round that up. So I would actually round that up to 86.0. All right. Now in that column, I can find my resultant component in the y direction by adding those three numbers. So I'm going to just say 86, which is 0.0, right? Plus 92.9 plus 51.4. And so the value of my component of that force in the y direction is 230.3 in units of newtons. Okay, now I'm going to go back and do the same thing with my x components. My first force is negative 150 times the cosine of 35. So the cosine of 35 is 0.819. And so that value is negative 122.85. Once again, 85 rounds up to 9. The next one, we have 0.342. And we multiply that by 120. That's a positive. So that number is 41. I'm going to circle that so it shows up a little bit. 41.0. Okay. And finally, we have 0.766 times 80. All right. So that value is 61.3. Now the last two values are positive, 61.3 and 41.0 are both positive, but the other one, the 122.9, is negative. So that means that my x resultant is actually a negative. So r sub x is negative 20.6 newtons. All right, So when you look at the table, you'll see that I've calculated both of those. I'm going to write my resultant as a vector, so it's r with an arrow over it, is equal to that number r sub x 20.6 times the I unit vector plus the r sub y component 230.3 times the j unit vector, and I have to put units. So it's that many newtons. Right. Now, if I want to write it in that form, that's mathematically correct. Your authors also like you to write it as a magnitude of a resultant at an angle. So the next thing I'm going to draw is an xy coordinate system, and I'm going to place a negative, a vector that has a magnitude of negative 20.6 in the x direction. That's at r sub x. And a magnitude of 230.3 in the j direction. And so I get a resultant that looks like an arrow pointing strongly off to the upper left quadrant. So the first thing I want to do is to find the magnitude of that resultant. So I take 230.3, square it, and take negative 20.6 squared. Of course, you know a negative times a negative is a positive, so we don't have to worry about that. But if I take that number and I multiply it by itself, this is really silly calculator, isn't it? But that's okay. So I'm just going to clear that entry. If I take 20.6 and add 20, multiply, pardon me, 20.6, that number is 424.36, and once again, even though it's negative, negative times a negative is a positive. So then I want to take 230.3 and square it, and that value is 53,038.09. Okay, so I add that number to the 424.36, and I get my radicand, a value of 53,462.45. And so the magnitude of my resultant is going to be the square root of that number. So since I don't have that function here, I'm just going to type in square root of 53,462.45, and it will tell me that the square root is, my resultant is 200, that's the magnitude of the resultant, 231.2 newtons. Now, one thing I want you to notice is the x component is so small that it doesn't contribute very much. In other words, the resultant is just slightly larger than the y component. And that's just sort of the way that the theorem of Pythagoras works. In other words, if you just have a short distance in one direction, it's not going to contribute too much to the overall number. However, the resultant has to be larger than the largest component, obviously, even if it's only a tiny bit larger. All right, so now I know that I have a hypotenuse of a triangle that is 231.2 newtons. So I draw that on my axes, and I want to find an angle. I'm going to find an angle with the vertical, and I'm going to call that angle theta. And I have r sub y, which is adjacent to that angle, and I have r, the magnitude of r, which is the hypotenuse. So if an adjacent and hypotenuse, that's a cosine function. So I can say the inverse cosine of the adjacent, 230.3, divided by the hypotenuse, 231.2. Okay, so I can find that value. I take 231.2 and divide that by, I'm going to have to do the reciprocal. That's all right. Let me do it again. I'm just going to clear it. Obviously, on your calculator, it's going to be a lot easier because you have more functions at your fingertips. But I just want to make sure that you can see my steps. So I have 230.3, which is the r sub y, 231.2 I divide those two, and that will be the cosine of that angle. So that means that I need to find the inverse cosine of that value. So I can say inverse cosine of, I didn't write it down over here. Oh my goodness. I'm going to pull this, no. Inverse cosine, there we go. 0.9961. 0.9961, and it will give me an answer of this many radians. But I don't want radians, I want it in degrees. Now you can convert back and forth between radians and degrees pretty simply. If you think about a circle has 2 pi radians, but it has 360 degrees, so that's your conversion factor. You can see that that's a very small angle, which what that means is that my resultant force is almost vertical, which makes sense because all 3 of the forces have a vertical positive component, so they're all adding together. But in the x direction, the 150 Newton force has a negative x component, so it cancels out, not fully cancels out, but it reduces the magnitude of the total. All right, everybody, well, that will get you through the second homework set. We don't have class on Monday if you're watching this in 2019, so our next class will be Wednesday. I also don't have the gradebook fully set up. I'm going to have to work with IT to get that done, so it may be Tuesday or Wednesday of next week before I get it set up. But suffice to say right now, if you turned in the homework, you have 100%. If you didn't turn in the homework, you have 0%, and you have the opportunity to turn it in late and get 100%. So I hope you will all take advantage of that. Thanks for your attention. We'll see you in class.